these boot camps are designed to kind of preemptively show you how everything works, and most importantly, how to do these calculations in Excel so that you can spend more of the time in the class learning what in the world's going on and less time trying to learn the tools and techniques that they kind of assume you already know how to use. And so let's jump into it. I'm going to jump into Excel, like here. And if you check out around page 56, as you know, there's two different lab manuals out there. So there's two different sets of pages. I'm just going to call it 56 though. You will see a lot of formulas they want you to know how to use in this exam, 2 pages worth. But for coming to the boot camps, you're going to learn that a lot of these formulas are actually unnecessary. And so I'm going to show you that this very first one, for example, binom.dis. It's my opinion that you should not bother wasting your time learning that one. And so if I were you, I would skip it. And when we get to the binomial session, which is next week, you will learn that everything you need to know how to do in terms of binomials can be done with this one formula. So it's of my opinion that you don't need that first one at all, because the bottom one is a lot easier to use and it does everything the first one does. So I strongly recommend you don't worry about it. Secondly, when we get to the normative boot camp, which won't be for about 2 weeks, we're going to utilize norm.dis. I don't know, maybe I'll sneak in a norm question next week as well. But you will use that function there to calculate probabilities for normals. And I'll talk about how we differentiate these things in a little bit. The last formula you'll actually need to know is norm.inverse. That one will allow us to calculate in reverse, inversing the technique. And so you'll learn that from me as well in the boot camps. But all these other ones, this whole entire rest of the page, is honestly, in my opinion, unnecessary. And so you will see me completely disregard the use of these. And so even though it looks like a lot, there's actually only 3 additional formulas they're going to expect you to know how to use, namely norm.dis, binom.dis.range, and norm.inverse. All that other junk you can actually ignore and just not focus on, because these 3 functions do everything you need it to do. But do notice that the new functions assume that you can calculate things like mean and standard deviation. So those old formulas, how to calculate mean and standard deviation, are going to carry over until this unit, which also means if I'm talking about mean and standard deviation, we're going to also need that one other calculation for z-scores, because this is all empirical stuff. So we're going to need that standardized command as well. And so occasionally you'll see me use standardize to do my calculations just the same. So now, what exactly is a probability? Well, believe it or not, you've already been doing probabilities in one form. There are mainly 2 types of probabilities. One that we call relative frequencies. That's the one we've been doing, right? And that's where you simply take some known amount, which we call X, we call it the observation, divided by some count. The other possible way of doing a probability is known as theoretical. Theoretical. I can never spell. Let's just pretend I spelled that right. Theoretical. I know it's not spelled right. I don't think there's an H there, but theoretical. And that's exactly the same thing. The only difference is you can't observe it because it didn't actually happen. It's like what would happen. So it's still X divided by count. But instead of calling it an observation, because it didn't actually happen, it's essentially what would happen. Believe it or not, we still call it an observation, but people get tripped up in the fact that you don't actually see it happen. And so the first one that we call relative frequency has a special name that we call empirical. And so if someone's talking about empirical probability, they're talking about something that actually happened. Versus theoretical is something like that, something that could happen. And so if I want a theoretical probability, it could be something like, what if I roll a dice and I wanted an even number? Well, it didn't actually happen, but we know there's a 1, there's a 2, there's a 3, there's a 4, 5, and 6. I know it's technically a die, but concept's the same. And of those numbers, I want even ones. So I want 2, 4, and 6. And so what would happen if we got an even numbers, there's 3 even numbers out of 6 possibilities. And so if you type that in Excel, you'll see it come out as 0.5. If we simply type equals 3 to, oops, I had page jump on, 1 second. Unlock, there we go, equals 3 divided by 6. And you see 0.5. That's all we're doing is just writing fractions when we do these probabilities. The difference, though, between theoretical and empirical, aka relative frequency, is the first one did happen. Let's say that we have these 1, 2, 3, 4, 5, 6 categories, like we stratified, and we kept rolling the die, and we just kept tally marks of how often certain numbers popped up. Something like that. And I want the probability of an even number based off what actually happened. Maybe we're trying to figure out, is that dice or die biased? Is it unfair? Because it should be around 0.5 to get an even number. But if we look at what actually happened with this real dice that we actually flipped and tossed around, we could see that in reality, there was 2, 6, and 7 times that we got an even number. Versus we already had those 7, so 3 more make 10, 13, 15. And so 7 out of 15 times we got an even number on actual rolls. And so that's 7 divided by 15, which is 0.46. And you'll see in general, if this prediction is correct, the reality will eventually get close to it the more rolls you do that. We call it the law of large numbers. The more you do something, the more likely what actually happens will approach what should happen in theory. And another name for theory, for those, depending on which instructor you have, you might also hear the word classical. These are treated the same way in this class. They're technically not, but as far as this class is concerned, we're going to treat them the same way. And so classical or theoretical is when you find a probability, which is just going to be some event out of the total amount of possibilities, is something that did not happen, where empirical, aka relative frequency, is something that actually happened. So in the first example, down here at the bottom, we didn't actually spin or roll the dice. We just looked at the possibilities and said this many even possibilities could happen. Where the empirical one, we actually supposedly rolled the dice and counted how many times the event we wanted to happen happened out of the total amount of rolls. But they're generally found the same way. Whatever you're looking for, divided by the total. And supposedly, the more you do something empirically, the more it will approach the theoretical in terms of the decimal. These numbers will get closer and closer and closer as you roll more often. It's called the law of large numbers. What you'll learn in test 3 content is how to compare these two things statistically to determine if the theoretical actually makes sense. We're actually going to do something called a hypothesis test, and that will verify whether or not these calculations are so different that we can say what we're thinking should happen is wrong, and it's therefore something else. But we're not there yet. For now, we're just going to learn how to find those two probabilities and make calculations. But that's what a probability is in a nutshell. Whatever you're looking for divided by the total. And it can be found by actual events or what we're thinking should happen divided by the total possibilities. And again, these other formulas, binom.dis.range, norm.dis, norm.inverse, we're going to learn in future boot camps, namely next week and the week after, and the week after that, because there's about 4 boot camps for this unit. But yeah, they're coming. You can ignore all the rest. Okay, let's jump into some questions and see all the stuff in action. I'm going to give less time to read these in general just because you've not seen these before. And a lot of this is new content, which is absolutely fun. Great. Those of you who have already got started, great job. So in the first case, we're looking for males. And so we can see, looking at the male row, we have 60 males and 45 males. And so we have essentially, just going to let Excel do all the hard math here. 60 plus 45, there's 105 males. But we need to know the total, right? That's just what we want. That's just the X. We still need our total count. And just so you have a reference, we often call count N because of the N in the word count. It's just a nice little shortcut. So if you ever hear people say N, they're talking about the total count. And so now we need the total count. And again, make Excel do all the work for us. 60 plus 45 plus 80 plus 60. And so we got 245. And so the probability I'm looking for is what you're looking for divided by the total. So the observation divided by the total. And that is my probability. Let's make that nice and bold so we can have it. And you can always adjust your decimals as you need to. This is definitely where you want Excel to do the rounding because these are not always pretty decimals, as you can see. And you pick whatever precision you have to give to the question so you get the answer right. But that is my probability of finding a male. And since this is an actual survey, they supposedly went through and surveyed people and asked, what kind of food do you like? Since this actually did happen, they would call this an empirical probability. It's from empirical data. It really happened. This is like a survey. We're not saying if we talk to 245 people, this is what they probably would say. No, we actually went and talked to people and got real data. So in other words, this is a relative frequency. Okay. Now the probability of females, just finding a female in the overall survey. Then we're going to do the same approach. But this time let's go a little faster. Let's use the sum command. Sum allows you to quickly add numbers by just highlighting them. So if I write the word sum and then highlight these two boxes, it will find the sum. And then like the count, if I say sum, I know I already did the count, but just to have it, if I highlighted all 4 boxes, closed it and hit enter, I get the sum. So you don't have to manually type all the numbers like I did here. You could just write the word sum and then highlight. Either way. And of course, you could type C3:D4 if you don't like highlighting. It starts at C3 in the top left and it goes to D4 in the bottom right. And then like before, we're going to simply take the top number, 140. What we saw is 140 females out of all people, which is 245. And there's the probability of finding a female. And there's another technique that we'll talk about later, I think actually next week, called the complement technique, that you could have found the same solution a different way. For now, we're just kind of getting our feet wet with finding probabilities in general and not worried about the real fancy stuff yet. Okay. Now, this next phrase right here, given that, it's a very special phrase. What that denotes is that we're changing the total. We're no longer saying, like on the first one here, right? The total, the count, we use those words synonymously in this case, the total or count was all people. Now that we're saying given that, the total or count is no longer all people. We're only looking at those who are males. And so the count is all males. So we're changing the denominator. And the way you reflect that mathematically is the first one, by the way, the A here, let's talk about that real quick. The probability of a male is we've written like this, P of male. And then the second one was probability of female. And notice how we're just saying the one thing we're looking for. But since we are changing the denominator in part C here, since we're changing it to have only males matter, we need to reflect that. And we do that with the following notation. We say the probability, we still want to find those who dislike spaghetti. But now we want the bottom number to only be males. So we put this straight line and say males. And so what that means is my denominator is only males. And so whenever you see a straight line like this right here, they're telling you that they're changing the denominator from all people or all things to whatever that subcategory is. So we're only looking at the male group. We're essentially saying that this other group doesn't exist. If we only look at males, how many of them dislike spaghetti? And so hopefully we agree it's 45. And then how many males were there? That we already found was 105, 60 plus 45. And so the probability that someone dislikes spaghetti, if they're a male, from our survey is 45 out of 105. And so we can go to an empty box, wherever we like, maybe right next to it, equals 45 out of 105. And there's our decimal. And I'll go 4 decimal places. Okay, the next one, straightforward, I hope, is saying how many people participated. They're looking for the total frequency. And we already know that. We found that a couple times. 245, right? So 245 people were surveyed. It's just all those numbers, all these numbers added up. So now for 3. Notice that it's different from letter C. There's no given that. So this means that we're still talking about all people. We're looking for that special category of female spaghetti likers out of all people. So we're looking for that intersection of female and those who like spaghetti. We're looking for this 80 right here. And so there's only 80 people who are female who like spaghetti. And since it's not saying given that for any category, we're assuming that it's talking about all people still. And all people is 245. And so then our decimal approximation, because they love decimals in this class, is 80 over 245. And just to be consistent, I'm going to keep changing all these to 4 decimal places, because often it's 4 decimals that they like. That's an arbitrary choice, but that's just generally what you're going to see, 4 and 3 for some reason. Okay. Let me erase my chart and let's keep going. So now we're looking for probability of being a female or being someone who likes spaghetti. So this or is interesting. It means that I'm happy if I find somebody in this category, or I'm happy if I find somebody in this category. The only category I don't want is men who don't like spaghetti. You could be a man who likes spaghetti, that meets that requirement, or you could just be a female, that meets that requirement. And so both those categories are acceptable as long as it just leaves out that one box. And again, we're not going to do complementary method right now. We're just going to focus on solving these directly. And this gets at an important concept that they're going to hit over your head with a lot in this class. And that concept is known as mutually exclusive. Whenever we see an or statement, you always have to think this. And so mutually exclusive is defined as the probability of both events happening. So we're going to say A, this N means and, B is 0. If it's 0, then all you have to do is take the probability of the first event and add it to the probability of the second event. If mutually exclusive. If it's not mutually exclusive, then we're going to do the probability of the first event plus the probability of the second event minus the intersection, that this statement up here, minus the probability of A and B. So we do this if not mutually exclusive. In other words, if they share anything in common, if they have a box where they overlap, then it's not mutually exclusive. If they have nothing in common, then they are mutually exclusive. So we like double negatives. Not mutually exclusive means that there is something in common, and mutually exclusive means nothing in common. So let's jump back to this question, females and those who like spaghetti. If I look at those who are female and those who like spaghetti, are there female people who like spaghetti? Yes. So they're not mutually exclusive. It's not mutually exclusive right here where they overlap. So we have to subtract out that value, that 80. So the probability for A means the probability of females, which we know is 140. We found it for part B, 140 out of 245. Probability of liking spaghetti is also 140, 80 plus 60, going downwards now, right? 80 and 60 is 140 out of 245. But the probability of being a female who likes spaghetti is 80 out of 245. And we found that right here. The probability of being a female and you want spaghetti was 80 out of 245. And so this calculation will be the solution that we're looking for. Now, a good question you might be asking is, well, that's nice and everything, but why do we have to subtract? Well, if you think about it, let's back up a step. When we found the probability of being female, we add 80 and 60, right, as our female group. And then when you found the people who like spaghetti, we add 80 and 60. But notice that we're adding this 80 and 60, then we're adding, sorry about that, I'll back out in a second. There we go. And we're adding this 80 and 60. This 80 and 60. So notice that this 180 down here is getting double counted. We're counting this 80 twice. We're counting it from the spaghetti group and the female group. And since we're counting it twice, we have to subtract off once to balance out. And we're subtracting off that 80 one time. And so that's what you're essentially doing when they're not mutually exclusive, is that you're going to subtract off that value that's being double counted. And so now let's just move things over, or maybe I'll just erase a little bit. I am recording this. You can always go back and pause if you need that formula there. So we would say equals, we're going to just type the whole thing in as it's written. Excel can handle it. So 140 divided by 245, 140 divided by 245, and then take away that 80 divided by 245. And there's our probability. It's the same probability that we could have also found by just adding up those three boxes. In other words, if I didn't want to worry about all that, they're going to ask you for mutual exclusivity, so just know you're going to have to do it eventually. But if you were desperate and you just can't remember the formula, you could have technically just added these three categories one time each and did 60 plus 80 plus 60 out of the total, and you'd get the same answer, because that's all you're actually doing. Technically, for the 60 and 80, we got the spaghetti, and then we're adding another 80 for the women, and we're just taking away that 80. And so you could have, if you wanted to, just added those three up and divided by the total, and you'll get the same answer. But just know they're going to ask you, are they mutually exclusive? What is the and statement? And you'll have to know how to do the process eventually. So it just depends, where you want to spend your time at. But if they're mutually exclusive, we just need to add the two probabilities up and you're done. If they're not mutually exclusive, you add them up and then subtract, and then you're done. And an example of not being mutually exclusive, probability of being a male and the probability of being a female. The males have nothing in common with the females. They are two different strata, right? Two different stratified categories. And since they're different, there's no overlap, they would have been just added up without any subtraction whatsoever. The probability of liking spaghetti and disliking spaghetti have nothing in common. You can't simultaneously say I like spaghetti and dislike spaghetti. I mean, technically you could, but in this survey we couldn't. So those are all separate strata. Okay. Probability of being a man and liking spaghetti is independent. So this independent has two different ways of doing the calculation. I'm going to show you what I think is the easier way. Eventually, not today, I'll show you another way of calculating independence. And of course, you get to decide which one makes the most sense to you. The test for independence is as follows. If it's independent, then the following must be true. The probability of the event you're looking for should be the same probability regardless if something else is the base. So in other words, the probability that it's hot outside should be the same probability that it's hot outside, even if you have homework. Homework should have nothing to do with the probability of it being hot outside. And so if they're really independent, then one category will not influence the other category. And so the common question I get is, how do you decide which is A and which is B? In general, it's just by convention, whichever one you read first. It actually doesn't matter. So when you're reading it, you'd first say, well, there's a man event happening, and then we have spaghetti event happening. And so that's the order you read it, so that's how you assign it. So the question we're being asked then, is it the same probability of finding a man in the survey? Is that equal to, we'll put a little question mark here, the probability of finding a man that happens to be a person who likes spaghetti? In other words, does liking spaghetti increase or decrease the probability of being a man? Maybe certain genders, like certain foods more than others. Chocolate, for example, statistically is more popular among women. And so if we found people who like chocolate, you're more likely to find a woman than a man. And so certain things like that may play a factor. Maybe spaghetti, has a gender distinction. And let's find out from our survey, at least. The probability of being a man, we've done this calculation already. It's 105 divided by 245. It's that 4286 number. So I'm just going to link it so we can have it down here by saying equals. I'm just going to go click on that 4286 number so I can bring it down below. And so that's the probability of being a man. It's just the 105 calculation that we did earlier divided by 245. Now we need a probability of being a man given that they like spaghetti. So remember, this part here represents the total count. So of spaghetti people, how many of them were men and so forth. So we need our total spaghetti category, 80 and 60, that's 140. Let me jump down. 140 people that like spaghetti, and then how many of those are men? So of the 140 spaghetti people, how many of them were men? 60. So 60 men out of 140 people like spaghetti. And so we find that fractional relationship. We just take the 60 and divide it by the 140. And you can write 60 divided by 140, whatever you like. Hit enter, and we get our decimal approximation. It's always good to make sure that Excel is not rounding these in a weird way. And so we're just going to bunch out to a bunch of decimals and see if they're exactly the same. If they are exactly the same, and that's very, very important, they have to be exactly equal, then you would say, yes, they are independent. There is no influence of liking spaghetti on determining gender. That's what we're determining. And if there's even the smallest decimal difference, like even if this one little 5 here was a 4 and this was a 5, we would say they're not independent. There is some influence, no matter how small. And so we have to make sure that they're exactly the same to be classified as independent. If there's any difference in the decimal calculation, then we call them dependent because they're not independent. In other words, one thing does influence the other thing. But in this case, spaghetti had no impact. So if you like spaghetti, you have an equal chance of being a male versus not being a male. Okay. We're trying to determine possible outcomes. I'm going to show you the long way so that hopefully you'll appreciate the shortcut that we'll do next. So when we're trying to find possible outcomes, one way of doing it is by a tree diagram. And so we're just going to go in order. We have this first event, then that's second, and that's third. I'm just missing the numbering, but that's what's happening. And so for our main dish, we have 3 possibilities. You could pick pizza, just call it P. You could pick tacos, or you could pick hamburgers. And then after that main dish, we have 2 options to go with your food. You could pick a salad or a fry. And you could pick that regardless of what you made the first time. because you can have pizza and fries, taco and fries, etc. So salad or fries. And then from each of these options, I could choose any of these three choices: ice cream, pie, cake. Ice cream, pie, cake, etc., etc., etc. I'm just going to try to squeeze it in. You'll see why I'm not a fan of this, because it gets kind of hard to draw without like really making it a lot larger on your paper, and it's just no fun, but that's okay. There. Whew. And then if I want to find out how many, I just need to count how many total branches I end up with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Looks like I miscounted somewhere. Oh, right there, 18. Yeah, not a fan of this way, but there are 18 outcomes. But what you may have noticed is I originally did 3 objects, and then 3 objects happened 2 times, and then each object happened 3 times. And so if you just do 3 times 2 times 3, you will also get 18. And that's beautiful. You can get the same calculation without all that craziness. And if you notice, there's 3 objects, 2 objects, 3 discrete objects. And again, when they're discrete, we can just times them together and you'll get the total outcomes. The only real advantage of doing this terrible drawing is you get to what we call the sample space, where we can list out all the ways it could work out. You could say, well, the first tree, PSI, means that you could have a pizza, salad, and ice cream. And then you could have PSP, pizza, salad, pie. And then pizza, salad, cake. And so essentially you can read the tree and get all of the actual individual outcomes. That's the advantage of doing a tree diagram, is it allows you to list out the sample space. And so if you were to write out the samples, the different ways it can work out, we call that a sample space. So they ask you for a sample space, they just want you to list out all the possible ways. In general, you're going to do things like that for small sets, like if it's up to like maybe 15 or 16 or less. They'll ask for a sample space. They won't ask for a sample space like 100 items, just because you don't have time in a day for that. So let's do the second one a little faster then. So this says numbers here. They actually really mean digits, or I guess I meant because I wrote the question. So we've got a 4 combination lock. So we know there's going to be 4 possible numbers. 1, 2, 3, 4. The numbers can repeat, so you can use the same number over and over again, and all digits are possible. So every number from 0 to 9 is possible. Now, often when people think about 0 to 9, they assume that means 9 numbers. But you got to remember that number 0 counts the number 2. And so if you look at 0 to 9, you'll see it's actually 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So don't make that mistake there. A lot of students see 0 to 9 and assume that means that there's only 9 numbers. Okay, so we know there are 10 possible numbers in the first choice. I could pick any of those 10 numbers. Since I can repeat, I can use the same number again and have 10 possible numbers the second time. I can again do the same thing and have 10 possible numbers the third time, and then 10 possible numbers the fourth time. And so like last time, I would make 10 branches, and then 10 branches, and then 10 branches, and then 10 branches 4 times. You do not want to make a tree diagram for 10 times 10 times 10 times 10 times 10. It will be a lot. So what we're going to just do is save us some time and just times these together. We have 10 4 times, and so one way of doing it is 10 to the 4th power, or just literally 10 times 10 times 10 times 10. Doesn't matter which way you do it. So again, I can say 10 times 10 times 10 times 10 like that. Or if you want to take some shortcuts, you can say this little arrow, which means it's the same number 4 times. It's all the same thing. The arrow is above the 6 key, so shift 6. You'll get the same answer either way. So on a 4 combination lock, there are 10,000 possible combinations using only the digits 0 to 9. We know a lot of locks actually go 0 to, I think, 60 or 30, in which case you get a lot more combinations. It would be 30 times 30 times 30 and so forth, or 60 times 60 and so forth. Last one here I know is very small, but the cool thing about pictures is you can grab the corner and make it bigger. So let's do that. Maybe scoot it down. This time I'll be a little bit more quiet, and I'm going to let you think about it for a minute and see how you would approach it now that we know the general strategy for this. So when I saw these questions, the first thing I do is kind of sketch out how many possibilities there are. By sketching out, I just mean draw, underline. So initially, we have the KW position. We have KW. And then we're going to have 2 or 3 additional spots. So 1, 2, and the possibility of 3. And it says they're going to be letters. So in the English alphabet, how many letters are there? For those who don't know, there are 26. A through Z, there are 26 letters. So when we think about it, for the first spot here, how many choices are there? How many letters can we choose from? Just K or W, just 2. The next one has to be any additional letter. It doesn't mention that it can't include K or W, so we are assuming all letters are possible. So there's 26 possibilities. In the next one, again, you're still required to do a letter, so there's 26 possibilities. It's this last box that trips up some people because they see or 3 additional letters, and so they assume it has to be 26. But it actually doesn't. Because you're getting the option of doing it. It's or 3. And so what does that mean? It means that this last box, because you have to put a letter here, you have to put a letter here. But in this last box, it could be a letter, or you could leave it blank. Because you don't have to do 3. And not doing something is a choice. You can choose to clean your room, you can choose to go to work, or you can choose to do nothing. That's 3 choices. So in this case, I have 26 letter options, or the choice to do nothing. So I have 27 choices that can go there. The other ones are required to have letters. You must do 2 letters, or you can do 3 letters. If you don't do 3 letters, then you made the choice to do nothing. So in this case, that 27 is what trips people up because they want to see 26 there. And so its product will be our calculation. And so the total number of ways it can work out is 2 times 26 times 26 times 27. And so for radio stations, there are 36,504 total ways you can list out call letters to radio stations. And that's without including things like numbers, Fox 105, and that kind of stuff. When you start including numbers, it gets even a lot more. Okay, let's keep it moving. So up here is our strata, our categories, and down here is our frequency. Nothing new from the previous unit. They essentially have 7 classes of strata, 1, 2, 3, 4, 5, 6, 7, and then we have frequencies for each category. And we're looking to find out the observations out of the total count. That's our probability, right? So in this case, we're looking at what actually happened. This is actually from a real semester, supposedly. So this is a relative frequency. aka empirical probability. And so we want to look at the people in the category or the strata of 5 or more. So we're looking at these categories right here. And this is the observation. These are the actual people. So our numerator, our top number, will be the 320, the 53, and the 41. And I will make that larger. That's just my numerator. And our denominator, of course, is just everybody. And unfortunately, it's a picture, so I can't write sum and do it that way. So we're just going to do it manually. If it wasn't a picture and it was a table, we would just write sum and add it all up like we did on the previous page. And so there's our total sum. All I did was add up each of the bottom row. And so now to get our probability, it's just what we're observing. 414 people or 5 or more divided by the total amount. Again, let me make my font larger. So 414 divided by 1601, hit go, and there's the probability that we're looking for. Okay. Now, you learned in the previous unit that when we say average, there are actually 3 types of averages: median, mean, and mode. But for this unit, when we say average, we're explicitly referring to mean. Mean, for discrete cases, is another way of saying expected value. So they could have also said, what's the expected number of classes? For discrete tables, this is a discrete table because we have whole number units and we have frequencies underneath it. So we have these whole number classes. So whenever we have something like that, we call it a discrete table. When you don't have a discrete table, mean and expected value are synonymous. For different distributions, they're not. And you'll learn about that later on, specifically when we get to the normals, that mean and expected value are different. But for discrete situations, we treat them the same. And so how do we find the mean and or expected value? Well, it's this fancy E-looking thing of x times P of x, and I'll explain what each part means. X we already know. That's our observation. That's what we're actually seeing. We're seeing these 47 students in that category. We see the 105 in that category. So those are the X. The P of X is the probability of being in each category, the probability of being a 1-class student, the probability of being a 4-class student. So we'll need to find the probabilities of all those calculations. And then what it's saying to do is multiply them, because when we write letters next to each other in mathematics, that means times. So we're going to times those 2 calculations. And then finally, this fancy E-looking thing just means add. We're going to sum it all up. So let's build our table real fast. And before I do that, I'm actually going to preemptively highlight my cells. Look at me being ahead of the game. And so we have our observations, actually our classes, 1, 2, 3, 4, 5, 6, and 7. And then we have these observations: 47, 105, 548 people, 487 people, 320, my bad, 53, and finally 41. And so we first going to use our sum command to get the total amount again, just so we have it handy down here. I know we already found it, but just good practice. You write sum, you highlight your data, and you hit enter. And there's your sum once again. So now what we want to find is we have our observations. We have the people for each category. Now what we're going to find is our P of X for each category. And so we're going to figure out the probability of each event. So P of X, the probability of each observation. And the cool thing is that we can quickly have Excel do that math for us. We're going to say equals. We're going to click the 47. And then we're going to divide it by that 1601. And like we did for relative frequency, we're just going to type in the total amount, 1601. And notice that P of X is a probability of X. It's just a relative frequency. It's just the frequency that we saw, 47, divided by the total. It's literally what you did for those histograms. And you're just going to do that calculation over and over and over again. Oops, one more time. There we go. And there's our calculations. And so notice again, P of X is nothing more than the relative frequency calculation that you did in the previous unit. And a good check to make sure you did it right is down here at the bottom right. If you look down here, whenever you highlight all of P of X, the sum should always be 1 because the sum of all probabilities always has to be 1. If it's not 1, you did something wrong. And so by highlighting all these P of X's, we can look down here and see that it in fact is 1. So we're good to go. So we found the X, or it was given to us really, but we found P of X. And so now we hit the times because you times before you add, right? That's order of operations. So just make some notes. We're going to do X times P of X. James is going to increase his font. Okay. And so we need to do X times P of X. So this 47 is the X times the 0.029 number. Definitely have Excel do these kind of calculations for you. And after you hit enter, we're just going to click on it, go to the bottom right, and pull it all the way across to get that calculation done repeatedly for you. So we now done X times P of X, and so our final stage, our mean, is simply to add them up. We want to do the summation, that fancy E looking thing, equals sum So let's go back, make it a little larger. You know what? I made a little goof. The P of X is right. So to be really clear for us, this frequency is not our actual observation because we're trying to witness, because we're talking about classes here. So that's where I goofed at, is that these are actually the values that we're looking for. We're trying to find the average of the classes. We still do our probability the same way, the probability of each event. But a person would say, I'm in 1 class or 2 classes or 3 classes. That's actually what the observation was. So I slipped up there. But let's fix it. So the P of X is right. You still do it by frequency, but it's the X times P of X where I messed up. I should have times that top row. When you write your formula, if you double click into it, you'll see it highlight these boxes for you. The cool thing is you can go to the blue box in this case, because that's where the 47 is. You can grab the corner, not the corner, but the top line of it, and you can physically drag it to the right place and fix your goof up like I just did. So if I take it from the 47 and drag it up to the 1, I don't have to erase and rewrite everything. Otherwise, of course, you can delete it, hit equals, and just retype everything instead. Same concept. But we're going to update this number, and then we're going to re-drag it across, and watch what happens to my mean when I do that. It automatically updates because it's summing up whatever's in that information. And so there's the actual information that we're looking for. And so if I check, my P of X is still done the same way. All that I changed was X times P of X. I changed what I'm trying to observe. I'm trying to observe the classes. And so I should have done classes and my probability. We added them all up and we came to 3.8, which tells us the average number of classes of students taking classes at this college is 3.8. So students are taking between 3 and 4 classes at this college. So there we go. So it's very important that we pay attention to what they're actually asking for. They're asking for classes, and so James should have realized that we're talking about this top row and not the bottom row. I found the average number of students, which doesn't make a lot of sense in the context of the college because they're a census. But that's okay. Okay, different ways of doing this question. I'm going to do it by our empirical classical techniques. And you'll find out next week when we do binom.dis.range or the binomial techniques that there's another way of doing it. And so we're trying to find a probability that all 3 children are from a blended family. And the first thing I want us to think about is Is birthing independent? Is birthing independent? In other words, does the first child's gender impact the next child's gender from a large scale standpoint? If somebody has a boy on their first birth, does that mean that their second birth is guaranteed to be a girl? Or is it independent of that? Well, of course, we know genetically the X and Y chromosomes determine it, and that had nothing to do with how the previous X and Y chromosomes were determined. So, in fact, they are independent. When they're independent, all we have to do is take each probability and times them together. When you want multiple probabilities, you just multiply the probabilities. That's all we need to do. So in this case, we want 3 children to all be blended. So the probability of the first child being blended will just times the probability of the second child being blended will times the third probability of the child being blended, because they're each going to be independently blended. Birth has nothing to do with the other. So when they're independent, we can just times them all together and rock on with the score. It is in the chat, Rena, and I will post it again at the end. You are logged in as a guest, and when you're logged in as a guest, it does not always show everything. So when you log out and log back into Teams normally, you'll find the spreadsheet that I'm using. So in this case, the probability of somebody being blended, it says is 18%. So we want 18%. Notice I'm writing 18%, not turning into decimal. Make Excel do the hard work. And you want that calculation 3 times. So shift 6, 3. You're going to have 18% 3 times. What that 3 there means, that little arrow. Same thing as doing 18% times 18% times 18%. So the probability of being blended and finding 3 kids that are blended, since they're all independent of each other, is very, very small. Less than 1% chance. In fact, 0.5% chance. Okay. Probability that none of the kids are blended. Well, if 18% is blended, then how much is not blended? Well, since this blended or not blended is binary, since there's only 2 options, if 18% is blended, then and all probabilities add to 100, then the remaining amount has to be not blended. And if you did 100 minus 18, you'll find out that's 82%. And so if 18% are blended, then 82% are not blended. And again, since these are independent, the probability of not being blended, not being blended, and not being blended will just be those 3 things times together. And so we'll end up with 82% 3 times. And there we go. That's the probability of not being blended, guaranteed from all 3 children. Now, at least 1 of the 3 children are blended. So remember what that means from Unit 1. At least means more or equal to 1. So you could have 1 child be blended, 2 child be blended, or all 3 child be blended. Those are all possibilities. And if we're going to do this a little more complicated way today, because we're doing it by empirical techniques and not binary, not binomial, we're going to focus on first making a sample space. This is something I could ask you to do since it's not a very large sample. It's just 3 children. And so first off, let's figure out how many that is. There's 3 children. The first option is blended or not blended, right? Blended or not blended. Next one could also be blended or not blended. And the last one could be blended or not blended. We times this together. 2 times 2 is 4. 4 times 2 is 8. There's 8 possible ways it could work out. So we could have it where they're all blended. We could have it where the first 2 are blended, the last one's not. Or the second one's not, and all of them are blended. Or the first one's not blended, and the last 2 are blended. Then we have the possibility that 2 of them are not blended in some combination. And notice I'm just moving the ends around. And then we have the last option of them all not being blended, 3 not being blended. And if we check it real fast to make sure we did it right, oops, I didn't hit enter. There we go. we can see it. There's 1, 2, 3, 4, 5, 6, 7, 8, which confirms with our 8. So there's 8 possible ways, and because I listed them all out, we call this a sample space. And we are interested in at least one of the kids being blended. So this has 1 being blended, 1 being blended, 1 being blended, at least 1, at least 1, at least 1, at least 1. So we technically need this probability, all these there, added up. We need to know all of those individual cases. And we can add them all up because they're all considered exclusive. You can't be the same different categories because it's different positions. Your last child being the not blended is different than the first child being not blended. And so they're all different in that sense. But there's a nicer way, and I guess now would be a good time to introduce the complement method. The complement method simply says you can do 1 minus what you don't want. And sometimes it's faster to get the probability of what you want. Think about it. If you have, a big piece of cake there, and most of it's chocolate, but one part is vanilla, and you don't like vanilla, the easy solution is simply to cut off the vanilla and take the rest. That's what we're doing. In this case, we want all of these calculations, except we don't want this one calculation on the top. So if we simply do 1 minus the probability of those 3 blended events happening, we will end up with the probability of at least 1. If we take out this one case, then everything else will add up to be what we want. That's called the complement method. It's nice when there's not much to subtract off. And so to find the probability of at least 1, it's actually pretty nice to minus the probability case of all of them being the opposite, all of them being blended. And actually, we want at least 1 blended, don't we? So I should have said that we want this one, because that's at least 1, and we don't want the not blended. Because this is what we don't want, since there's not 1 blended child in that group. Turns out the probability technique is still the same, so I should have just not blend it, not blend it, not blend it. And so that probability calculation, what we're looking for. So let's do that. The probability of not being blended 3 times, we already found, right here. It's the probability of not blended. And so if we just do 1 minus that, we will get the probability that we're looking for. 1 minus not being blended is 0.448632. And again, if you found all these probabilities and just add them up, you would get the same solution because all probabilities add up to 1. That's the cool thing. But definitely when you have these at least cases, it's often easier to use the complement method. Just 1 minus what you don't want. Okay. I took the liberty this time of setting up the table on the far right so that we can see it when we answer these questions. I'm going to guarantee that my font here is sufficiently large. Close enough. Maybe scoot these up. Okay. And so the first part here states that what's the probability that the following table states that the probability of having 6 children is 2 out of 5. Does this make a discrete distribution? In other words, we're saying the probabilities add up to 1. And so if we go in here and put 2 out of 5 into that 6 box, are these probabilities going to add up to 1? Now, I already took the liberty of starting it for us. I found the sum of what we currently know. And so those 4 boxes that we have are the information. And when we add more information to 6 here, we can see if this will break over 1. If it goes over 100%, aka 1, it means that the probability is too high. So if it's something like 8%, it's still okay because we can then find 7% and we have 100%, so everybody's happy. But if it's over 100%, it's no good. It's not a discrete distribution. So let's see, 2 out of 5. And look at that. That's way too much. All probabilities add up to 1. And so it can't add up to 125. That's too much. So would this be a discrete distribution? No. Simple enough. It's over 100, over 1. So instead, what they're saying, that's what his line's here. They say, well, instead, the probability of having 5 kids is 3 out of 100. Finish the table. So we're going to remove that answer to number 6. And in that box for 5, we're going to write 3 out of 100 equals 3 out of 100. Excel just knows to get the percent because everything else is a percent. Excel is pretty smart. And so we got to figure out this last number. What number would go here to make this whole table equal to 100%? And so we could just do 1 minus what we know. We can just use the complement idea. So 1 minus 88% will leave what's left. Oh, I made a cell reference. I should have typed that out. 1 minus 88%. And there we go. So that 6th cell would be 12% if 5 is 3%, because all probabilities add up to 100%, aka 1 whole. And if that's 3%, then that has to be 12% to even out. So we've done 1 and 2, so now let's go on to 3. What is the probability that someone has 2 or 3 children? Well, now let's think about it. Is 2 and 3 mutually exclusive? And the way we tell from a table is draw lines through each category. If the lines cross, then we'll have to do that technique of the probability of A plus the probability of B minus the probability of A and B, where they overlap. If they don't overlap, then you just have to add them up. And in this case, my lines are parallel. They're not overlapping. The 25 and the 30 lines don't cross, which means the probability of being 2 or 3 is just their summation. So for number 3 here, just want to write in the right spot, I would say the sum of 2 and 3. And of course, you could just write 25 plus 30. If you can eyeball and know it's 55, that's fine. But 55% is what we're looking for nonetheless. Okay. We're looking for expect. And so we're trying to find, first off, the expected value. But notice it's kind of written a little different than before. We're not told to find the average number of kids, right? We're not saying how many kids do we would expect to have. We're having this extra condition of at least 1 child. And so in this case, we're defining expected value a little differently than just simply the average. So we're looking for the probability in a very specific case, because in general terms, we know it's the summation of x times p of x. But this is when we're talking about all cases, all children in this case. But now we're adding this extra condition of at least 1 child. We're defining this probability very precisely, in which case we fall back on another definition of expected value, and that is n times p, where n is the number of that group we're looking for. So we're looking at 1,000 families, and then we need to find the probability of at least 1 child. So we're going to find that one more closed case. So it's a little different than the one above, because the one above would have been more of like, what would be the expected number of children? And that's it. That would refer to the overall group of children. But when we confine it to a certain situation, it becomes n times p. When we have like at least 1 child, probably of 2 children, that kind of stuff. Or how many would you expect to have, more than 3 kids? Those kind of phrases where you're not using the overall population. So we already know the n, we already know 1,000. We just need to find the probability of at least 1 child. And we can do it 2 ways. We know that at least 1 child starts at 1 and goes all the way to the right. So I could add up all these probabilities, or I can use the complement and just take out the 8 from 100. Same thing, right? Because the complement just takes off what you don't want, leaving what you do want. So we already know n. That's told to us to be 1,000. And we have p, which is essentially 100% minus 8%, which is 92%. N times p will be our expected value, because we don't want the whole population here. So 100 times 92%. I'm just clicking cells, hit enter, and there's 920. So of 1,000 families, we would expect 920 of them to have at least 1 child. and 80 of them to have no children. And there you go. Checking the chat real quick. Okay. Now, something that people often care a lot about, playing the lottery. So let's put together some information that we know. We first need to figure out the probability of winning, which of course is what you want divided by the total count or possibilities. And we need to figure out, in this case, how it goes. Well, in terms of winning, there's only one winner. So there's only one winning ticket. But we got to figure out how many tickets are being sold. What's the count? Well, we see that there are 4 possible numbers. 1, 2, 3, 4. And though it doesn't simply state the range of numbers, we're going to assume digits here, because otherwise there's infinite numbers, right? Because we don't know if it's like from 1 to 100 or whatever. So we're just going to assume simplicity here and just say digits. That's often what they mean if they don't give you a range. Otherwise, they'll say numbers from 1 to 30 or something like that. So if we assume digits, and digits go from 0 to 9, we know there are 10 digits. And there's no mention about not repeating numbers, so we have 10 digits each time. So 10 times 10 times 10 times 10. If we times that all the way out, we get 10,000 tickets. 10,000 possible right answers, with only one being the actual right answer. And so 1 out of 10,000 is the probability of winning. Let's actually get that decimal approximation. In this case, it's going to be precisely, but that's okay. And poof, we have the probability of winning. Well, losing simply means not winning. So we could do the complement method to get losing, 1 minus winning, right? And so if there's like a 0.0001 chance of winning, then there's a 0.9999 chance of losing, which means you're almost guaranteed to lose. And so expected value of winning, be very careful here. What does it mean to win, or expected value of playing, I should say? That's a fun thing to think about. So essentially what we're going to figure out is the expected value of winning, and we're going to take away how much money we think we would lose. And so we're going to find the expected value of winning minus the expected value of losing. And so what would be the expected value of winning? Well, if you win the lottery, you win $1,000. But did you actually win $1,000? No, because you had to pay for a ticket. So if you win, you actually only win $999 because you don't get that $1 ticket back. And then the probability of winning, because remember, N is our payout, times our P is 0.0001. Where if you lose, the expected value of losing would be, you would lose that $1, right? You would minus the $1. That's why we subtract, because you're losing the money. And then the probability of that $1 being lost is 0.9999. And so there we go. If you lose, you just lose the $1. If you win, you get $999. So let's type it out. If I win, I get $999 times the probability of winning. You can click the cell or you can type it out, whichever way you prefer. And if you lose $1. And the probability of losing is this 0.9999 number. So if you play the game, you should expect to lose. Let's click on the home and the dollar sign. You would expect to lose 90 cents if you play this game. And in fact, I don't like accounting style. I'm going to go currency. That makes more sense to me. So if you lose, you're going to lose 90 cents every time you play, because you should expect to, in other words. Don't expect to win playing the lottery, is what they're kind of saying. And every time you play, you should lose about 90 cents on the dollar that you give them, because there's that chance of winning. So that's why it's not a pure dollar. And then if you play it, in this case, 6 times, well, that's literally 6 times how much you lose. You would expect to lose 6 times the 90 cents. And so if you play the game 6 times, you would lose $5.40. That's how much you would expect to lose on average. because there's that chance that you would actually hit it big and win. Probabilities against you, which is why you only play the lottery if you want to have fun, right? Because you don't expect to actually become a millionaire or a billionaire or whatever. You hope to, but probability is not in your favor. And that was just using digits. Imagine if it's like the real lottery where the numbers are like from 1 to 60 or 1 to 75. Then the probabilities shrink even more, which is why they can afford to give such a massive payout, because the probability of winning is so small. Okay. So we have actual batteries being used. So we now know this is an empirical situation. The previous case, let me just back up for a second. We didn't actually play the lottery, right? We're finding out what would be the probability of winning, losing. So this one would be classified as classical or theoretical. Theory. It's classical or theoretical because it didn't actually happen. While this one actually did happen. Someone actually went and tested. It did happen. So we would call it empirical, aka relative frequency. This is a nice distinction to make. It doesn't actually matter for this unit. In the next unit, it's going to become a bigger deal because you're going to compare classical to empirical to make decisions about hypothesis testing. But that's not yet. Just like to bring it to your forefront because they are going to ask you, is this a classical technique? Is this an empirical technique? And you have to know the difference. And when I say classical or theoretical, they mean the same thing for this class. Okay, so 4 batteries failed the test. So the probability of finding a failing battery would be 4 out of 15. The probability of a good battery, let's use G for good, is the rest of them, right? So if 4 are bad, that leaves 11 to be good. Because batteries are either good or not good, right? They either pass or didn't pass. And we're getting 2 random selections of batteries, and we're going to find the probability of each case. So the course question you got to think about is, are these independent? Is the probability of being a good battery for one case distinct from another battery? Because we have no evidence otherwise, we are going to assume independence. And you'll find out later on when we have to assume not independence. So we're going to assume that they're independent, which means you can just times the probabilities together. So if they're both passing, they're both good. So 11 out of 15 times 11 out of 15. Oh, wait, they're not independent. Do you see why? What gave that away? Why is it not 11 out of 15 twice? It's this phrase right here. And that was actually what I was hinting at where I said that they're going to find out later, but they put it right in there. That implies that it's not independent. Why is that? Well, that means that when you pull out a battery from the batch and you go back into the bag again, there's 1 less batteries. So if I have 15 batteries, 11 of them are good, so I'm going to call 11 X's. And then 4 bad ones. When I pull out the first battery, there was 11 out of 15 chance that I could have that battery, but that battery is now gone. And now notice there's only 10 good batteries left. And because that 1 battery is gone, there's only 14 batteries in there. So when we see without replacement, it's not independent. We still multiply our probabilities together because multiple probabilities is multiplying. But notice that the denominator, the base, changes. Not always the numerator, but the base will always change because there's 1 less item each time. So in this case, we have 11 15ths times 10 14ths. 11 15ths times 10 out of 14. Just write the whole thing in straight. And let's fix our decimal because I'm pretty sure that's not 0.5. And look at that. Always check your decimals. Next case, they're both failing. So initially we have 4 out of 15 that are bad. We're not replacing it, so now there's only 3 bad ones, and there's 14. Because we didn't replace it, we lost 1. So 4 out of 15 times 3 out of 14. And there's the probability of failing. Now, at least one battery failed the test. So it could be fail, 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 good, good, fail, or good, good. If at least one battery failed, we want this group right here, which means we could just do 1 minus the good, good case, right? We can just take the complement. If we take that out, that will leave what we're looking for. So we would say 1 minus the good, good case, which is the one we already calculated up here. It's 0.5238. And just so you see it, let's actually do it the other way. Let's find the probability of these three cases and then add them up and see that it's the same answer as that one. So the fail-fail case we already did. This was fail-fail, right? Because they both failed. So we did that one. The probability of being fail and then good. Well, the probability of having a failed battery is 4 out of 15. The probability of being a good battery, because you took a failed out, it still has 11 good ones, but there's only 14 batteries left because you took one out for the failed one. And that's your failed category. And then good, then failed. Well, initially there's 11 out of 15 batteries. You take out a good battery, so there's still 4 bad batteries, but now there's 14 total batteries left. And so if I take the failed plus the failed good plus the good failed, notice that you get the exact same answer. That's why we like the complement method, because it's just a little easier, a little faster. But in the end, it really doesn't matter which way you do it. You can either do the complement and just subtract off what you don't want, or you can add up everything that you do want. The solution is going to be the same either way. All right. 69% of adults will have some kind of care. Among those, 20% will need long-term care for more than 5 years. So let's think about it. The probability of needing care is 69%. And then what does among those mean? Well, that means of that group, aka given that. So it's another way of saying given that, which means the probability that you need long-term care, given that you need care in general, is 20%. That's what the two probabilities above are saying. 69% of anybody in that age range needs adult care, some form or another. And of that group, of those 69% people, 20% need long-term care. Okay. So now it says, what's the probability that someone over 65 will not need long-term care? Let's think about what they're saying now. We're talking about the overall population of adults, right? And 69% need long-term care. So I should probably be more careful with my 20% in long-term care usage here. I mean long-term care for more than 5 years. So they need more than 5 years, given that they need long-term care in general. Just to be a little more precise. Statistics is all about being precise, right? And so we're looking for any from the overall population, how many don't need long-term care at all? Well, if 69% do need long-term care, right? They need some form of long-term care. The amount that don't is just the complement. So in other words, 1 minus 69%, or 100% minus 69%. That's the same thing. And we see it's 31%. So 31% don't need long-term care at all for anybody over 65 in some form or another. Now it's saying, of the overall group, how many need long-term care for more than 5 years? So we got to think about that very carefully. They're not saying, given that you need care, how many need care for more than 5 years? That would just be 20%, right? It's saying that what would be the probability that you need long-term care from any adult, so including those that are not long-term care. So essentially what we're trying to find out is what's the probability that you just need care for more than 5 years, regardless if you need any kind of general care, regardless if you're in this category or not. So one thing to think about though, or notice, is that we have the probability of more than 5 years, which is what we're looking for, out of any kind of long-term care, and we have the probability of long-term care. Notice if we times these together, if you divide and times by the same amount, they cancel out. In other words, if I had like 3/4 times 4, the 4s would cancel out, leaving just this amount on top. It's essentially what we would do. So if we just take our two probabilities and times them together, you cancel out this other factor of long-term care in general, leaving only those who need more than 5 years of care. And so in other words, if we just take our two probabilities and times them together, we will be left with the probability of needing 5 or more years of care, given that you're an adult who's 20 years, sorry, an adult over 65 years old. It's at least 13.8%. Just times those two probabilities together, because you want to get rid of or cancel out the long-term care category and just look at the overall population of more than 5 years. And there's another way of doing that question, and I'll show you later on when we get more into independence. Not today. Okay. Now it says, what is the probability that less than 5 of them will need some variety of long-term care? So now let's think about this. In order to answer this question, we're going to save this one actually for next week, because this is going to use a binomial technique. And we're not doing binomial just yet. And so I'll bring this question back next week. Essentially, there's a technique called binom.dis.range, but I'm not going to go into it today because it's already 10:23, and this would be a lot longer if I start including binomial stuff. So I'm going to save this one, make a note for myself, save for next week. And that's when I'll show you how to do binom.dis.range stuff, including answering this question. So let's move on to the next page. Okay, 50 people were surveyed, complete the table. If we go through and look at the table, we can see by adding them up that there are, in fact, 44. And so if there are 50 total, then we just know that missing number is the amount to make it whole. And so we can see that there are missing 6 people. If I add them, highlight it again, look down here, I can see that the frequency, the total sum is 50. So we did the first part. Yeah, I did correct this one. I saw that that should have been a frequency and that should have been X there. I fixed that over here for us. And then it says a randomly selected person was chosen from above. What's the probability that at least 2 have children? So at least 2 means 2 or more, right? And so we need to find the probability of this group. So let's go ahead and find the probabilities of each of them. And we'll first do that by finding the sum of our frequencies. So we know how many people were surveyed, 50. And so now we want to take each frequency and turn it into a relative frequency. So we're going to simply divide each cell by the total amount, in this case 50. Run it all the way across. Check my sum down here and make sure it adds up to 1 so I know I did it right. And it did. It says 1, so we're good. And now it says we're going to find the probability that at least 2 be children. So we're going to sum up at least 2, so 2 or more, all the way across, close it, hit enter, and there it is. 52% had at least 2 children or more. Randomly select a person which chose from above, probability they would have more than 2 children. So what is the difference between at least 2 and more than 2? Well, more than 2 means it can't equal 2 because 2 is not more than 2. So it starts at 3 and it goes bigger. So more than 2 means the same thing as 3 or more, if we're talking about discrete numbers at least. And let's just double check our decimals. And yeah, that one's safely 0.3. Less than 4 children, some less than 4. So of course that means 0 through 3 is less than 4. Summed it up, and there's our probability. So you're more likely to have less than 4 children because it's closer to 1 than you are any of the other two options. The more close to 1 it is, the most likely the event is. The closer to 0 it is, the least likely the event. So you're least likely to have more than 2 children, and most likely to have, from these 3 options, less than 4 children. Okay. I'm going to move these answers down just because I'm going to need the space. Because this last question here, and in particular this part right here, this is going to be the longest calculation you're going to do in this test. It's the longest one, so it's the one when you see it, know it's going to take you a minute. Not hard calculations, just long calculations. And we already know the generalized mean, aka expected value, is the summation of x times p of x. And that's how we would symbolize mu. And I know it's getting close to 10:30, so if you have to go. I will stay and finish the last of these questions just so you have it all on video for you, but I understand. I appreciate you hanging out. Anyways, that's our mean calculation. And the standard deviation calculation is a little more. It is going to be the summation of x minus our average, our mu, squared times p of x. And I will show you step by step when we get to that part, each of the calculations. It's not hard calculations, as you'll see. It's just a lot of them. In fact, if you notice, there's 1, 2, 3, 4 calculations in order to get this answer. Luckily, Excel does all the hard work. You just got to remember the steps. And I'm recording the steps, so you can always go back and get it. But notice before we can even do this calculation, we always got to find the average. And so let's get this average done like we did before. So we're going to do x times p of x. Always write notes so you know what you did later on. And so equals x, the very top row, James. I did that wrong last time, didn't I? Times p of x. Take that all the way across to the right to get those calculations all done for us. And then once you do x times p of x, what do? We sum it up, that fancy E thing. So let's sum it up. Our mean will be the sum of x times p of x. Oh, and I forgot one last part of that formula. This is just variance. And when you add the square roots, we now have standard deviation. Variance is the inside part. As we know, if you take the square root of variance, you get standard deviation, as I showed in the previous boot camp. So x times p of x is that calculation. We found the sum. So here is our needed mean. It's going to color it yellow. Let's see if there's any decimals involved. Sometimes there is, sometimes there isn't. But no, it's nicely too. So that's going to make entry a little easier. But now we have to do the next parts. We want to get standard deviation. So the first thing we do by order of operations, if you remember them, please excuse my dear Aunt Sally, right? We're going to focus on anything in parentheses. So we're going to do this step first. X minus the mu, X minus the average. So that would be our first step. Then it's going to be X minus mu squared, because the next thing we do in the order of operations is squared. We're going to take care of the exponents next. Then we look for any kind of multiplication or division, and that's times p of x. So let's make a note of that so we know what we're doing. So we're going to do x minus mu squared, but times p of x. And then once we do all that, we can then finally find the sum of x minus mu. I'm just writing out the steps so we know what we did later on. And then finally, we can take the square root of the sum of x minus mu squared times p of x. Told you, it's the longest calculation you're going to do in this class, or not, at least in this test. There's probably one that's a little bit longer, but it's actually not as bad in terms of steps, at least. Excel does more of it for you. And so we're going to do these steps in order to get our standard deviation. And whatever ends up being down here, I'm going to call it yellow. That's our goal. This is our standard deviation down here. And so let's do it. We first want to do x minus the average. We know x is the top row. We're going to minus the average, which is this 2. Because 2 is a nice number, there's no decimal with it, I could just write 2. If it wasn't a nice number, what you would do is click on the cell, and then you want to lock it so that it never changes. Otherwise, when you drag it, it'll mess up your calculations. In order to lock the mean, you put $signs around it. The $signs tells Excel, don't change that cell, but change the other one. That way, when I drag it over, notice it says M2, then it says N2, and O2, but every time it says T5, T5, T5. That part doesn't change, it's T5. So when you lock something, one cell won't change, while the other one that's not locked will. In this case, since it was a nice 2, you could just type -2 just the same, but it won't always be a nice number. So get used to locking cells. So that's x minus mu. Now we're going to take the calculation we just did, x minus mu squared, times the p of x, the 0.2, hit enter, and then take it all the way down. Do all those calculations over and over and over again, in other words. Now we're ready to sum it all up. So equals sum, parentheses, and select your values. Find the sum of those values. That there, my friends, is the variance, if they ever ask you, and the square root of the variance, SQRT, of the variance, that is standard deviation. So the mean is given as 2, and the standard deviation is 1.755 to whatever kind of precision you need it to be. I'll just assume 3 decimal places in this case. So if I want to represent it symbolically, I could say that the mean was 2 and the deviation 1.755. But again, not hard calculations. We just times, we subtracted, we squared, we timesed again, add it, and then finally square root it. They aren't hard calculations, just a lot of them. So definitely write notes and keep this in mind so you can do the calculations yourself, but those are the steps to doing them. All right. We're trying to find out, having no dents and no cuts, is that mutually exclusive? And we're going to prove it mathematically. Remember, mutually exclusive is defined as the probability of A and B equaling 0. And we know if it's not mutually exclusive, then the probability of A or the probability of B will equal the probability of A plus the probability of B minus the probability of A and B, because this amount is not 0. So when it's not mutually exclusive, that means the probability of A and B is not 0. And so if it's not mutually exclusive, not ME, we would solve the OR statement this way. And if it is ME, we would do the probability of A or the probability of B this way. We would just add them up and call it a day. It's whether or not you need the extra step of subtracting. And it should make sense why you don't need the subtraction step, because if they're mutually exclusive, it's 0. And subtracting 0 doesn't do anything, which is why we just leave it off. And so now let's think about what's being told to us. We have probability of having no dents, right? No dents. So the probability of no dents, that is 0.94. And the probability of no cuts, that's 0.931. Oh, no, it doesn't. My bad. Can't read. The probability of no cuts is 0.99. This one says the probability of no dents and no cuts. The probability of no dents and no cuts is 0.931. Okay. Well, if we're going to prove this mathematically, all we have to figure out is, can we do the probability of A or the probability of B? That would mean that if I do the probability of no dents, and no cuts, can I do 0.94 plus 0.99? Is that possible? Think about it for a second. Think about what we learned so far about probabilities. Can I add 0.94 and 0.99 and get a probability? Throw it in the comments if you're still here. Can we do that addition? Yes or no? Binary options. Throw your best guess. I'll wait for at least one person to answer. You're right, Rena. And the reason why is that this counts as a probability. And we know all probabilities should be less than or equal to 1. And if we add 0.94 and 0.99 together, we don't get less than 1. We get way bigger than 1. We get 1.93 if you add those up. And so that's not possible. But we know these probabilities are true because we're being told these probabilities. That means that there is some subtraction, this probability of A and B happening. And in fact, we were told what that probability is. It's 0.931. And so in fact, we know by default, it kind of told it to us without saying it so much, that there's this extra value here that's not 0. Namely, this value, this A and B, is 0.931. And so there's a subtraction that's happening. And since it's not equal to 0, since this is not equal to 0, we know it's not mutually exclusive. And so even without knowing this number, even without being told it's 0.931, because these two probabilities are over 1 if you add them up, we know by default it can't be mutually exclusive. And so you would say it's not mutually exclusive because 0.94 plus 0.99 is greater than 1. That means that there has to be some subtraction amount. So even if we didn't know this amount, it was just some unknown number, we know we would need something here in order to make this less than or equal to 1. And so it's impossible with the given information. Of course, we're told right away that this amount exists, and therefore it's not mutually exclusive by definition. We already knew that, but they didn't ask you by definition. They want proof mathematically. And so the mathematical statement that you would argue is that it's more than 1. If they said justify by the definition, you would just say this claim. And so this is by definition. And they'll sometimes ask you by definition, in which case you just got to show, well, by definition, it's not 0, therefore I'm done. If they didn't ask for the definition and they want it proof mathematically, you have to show that the two values they're talking about is more than 1 if it's not mutually exclusive. If they're exactly 1 or less, then they're potentially mutually exclusive. It depends on the and statement. All right. Part B here, we're looking at or, which again, we already know is the addition statement. And because it's not mutually exclusive, we're talking about the statement down below here. So we just have to finish the question now. It would be equal to, make my font so y'all can read it. It will be equal to 0.94 plus 0.99 minus the mutually exclusive value of 0.931, the value of the and statement. And let's fix our decimal just so we can see it. And there it is. It's not exactly 1. See how it tried to trick us? Try to tell us it was 1. Always check your decimals to make sure that what the actual answer is. It's actually 0.999. So it's about a 99% probability of getting a good box that has no dents and no cuts. Not my experience, but that's what they're saying the probability is. Must be a really good company. My Amazon boxes are always messed up. Okay. Due to time, I'm going to answer this one a little faster, but hopefully we'll get what's going on. And I'm not going to worry about the Excel calculation. You can always type it in Excel. I'm just going to set it up to show you how to do it. So the first group here, we have replacement, which tells us that we can do independent calculations. The next one's without replacement. So we're going to have to worry about dependency, which just means that the denominator or possibly the numerator are going to shrink each time. And now let's first find our total count. So we can see that we have 6 orange, 4 red, 5 blue, 2 yellow, 4 violet. So 21 total flowers. Just added up the colors given. And we want to find multiple probabilities because we're finding multiple flowers. So we're going to multiply. So 3 orange flowers with replacement. So there's 6 out of 21, but you're replacing it. So you're going to put the flower back and grab again. So 6 out of 21, 6 out of 21. It never changes when you do replacement because they're independent. On the other hand, if I have 6 out of 21, when I don't replace, I now have 5 oranges and then 4 oranges. And it goes down by 1 total flower each time. So without replacement, the denominator will always decrease. The numerator only decreases if it's the same strata, if it's the same category. Now we have a red flower initially, and there's 4 of them. It's not going to do replacement, so I'm always going to have 21. That will never change. And then blues, there are 5 blues. So independence, you notice, is nice. There's a lot less thinking. You just write them down, and that's it. Try and make that 5 a little more legible. And boom. In this case, we have 4 out of 21. Then we know we're always losing a flower, so I'll go 20, I'll go 19. And then that's the red flower. And then how many blues are left? Well, all the blues initially are left. But then you picked a blue, so there's 1 less blue. For the violets, we have 2 violets and then a red. So we're going to have 21 all 3 times because replacement puts them all back every time. 2 violet, so the violet would be 4. 4 violets each time. And then the red, that's just 4. Great. Here we know we're not doing replacement, so 21, 20, 19. And initially we have a violet of 4 of them. You picked a violet, so there's 1 less violet. Now you go to red, you didn't pick any reds yet, so there's all the reds still there. Yellow flowers, there's going to be 21 every time, and you're going to keep putting that flower back so you can possibly pick the same one over and over again, so there's 2 each time. Something cool happens on this one. Again, we have 21 flowers, then 20 flowers, and then 19. We have 2 yellow flowers. You picked one, you don't put it back. You got 1. You picked one, you don't put it back. And now there's 0 left. Well, 2 times 1 times 0 is just 0. And that should make sense. It's impossible to get 3 yellow flowers when you only have 2 of them. So, of course, you don't have enough yellow flowers to get that many. And if you want a decimal approximation, again, just remind us, let's look at part B here. So I just type one of them in. For 9B, you would type them in just as they're written. So 4 out of 21 times 5 out of 20 times 4 out of 19. Just type them in literally how they're written. Hit go, and there's your probability. Okay, last one. And thank you for those who stuck out the whole time. I know I went over, sorry, but there's a lot of stuff in this unit, and I'm doing my best. Okay. Notice in this question, we have the OR statement. So your brain must immediately think mutually exclusive. We know if it is, we can simply add up the 2 statements, blue and red, and be done. If it is. If it isn't, then we have to do the subtraction step. The good news when you have a table, it's really easy to know if they're mutually exclusive or not. All we do is draw lines through that strata and see if those lines cross. Through blue, through red. Do my lines cross? No. That means that we get to utilize the mutually exclusive property. We can just add them up. So we're just going to add blue and red up. And we know total blue is that 151 and total red is the 101. So probability of blue, that's 151 out of 500. Probability of red, that's 101 out of 500. And because they're exclusive, adding them will be sufficient. So 151 out of 500 plus 101 out of 500. And there we go. Always check your decimals because Excel likes to round things off. And look at that, it's not exactly 0.5. Okay, another OR statement. So we're going to be very careful. We're going to draw some lines through white, boom, and through coupe, boom. The lines cross. So this is not ME, or this one was ME. First one was ME, second one's not ME, which means that we have to use that second formula. The probability of white plus the probability of coupe minus the probability of white and coupe. But the good news is we have all these values. We know the probability of white is that denominator, the total value at the bottom, that's 61 out of 500. Let me first make my font nice and large. One day, I'm going to be a grown-up and remember to do that for y'all. So white is 61 out of 500. Probability of a coupe is that in there, the 125. So plus 125 out of 500. And we need to minus where they overlap. And they literally are crossing right there at the 5. There are 5 cars that are white and coupe. So 5 out of 500. It's where the lines cross is your mutual exclusive part. And so now we are done. We have the probability of white, probability of coupe, minus white and coupe. Hit enter, and there we go. That is our probability of a white or coupe. So you just take your probability of white, add your probability of coupe, and subtract where the lines overlap. They overlap at 5, so we subtract it off to 5 fraction. Woo! All right, my friends, that is classical empirical probability in a nutshell. Next week, I'm going to introduce the binomial concept. Week after, I'm going to introduce the norm.dis or norm distribution concept. And then finally, we'll end it off with the central limit theorem. And then, believe it or not, it's time for a test. So we have about 4 boot camps before your next test. This is one of those 4. Because next is binomial, and then norm, and then central limit theorem, and then test time. Hope this information was helpful. I did record everything, so you can always go back over it and check it out.